We're going to spend the rest of the semester essentially talking about hydraulic fracturing. And we're going to talk about the mechanics of hydraulic fracturing and hydraulic fracture models, other things. But I wanted to have at least one lecture to just discuss the impact of hydraulic fracturing and sort of the big picture, because this is something that many of you probably know. Honestly, it's likely one of the motivations you picked this major, right? You're all young enough that you chose to go to college after the shale revolution, right, with some knowledge of it. And of course, that's fueled by hydraulic fracturing. So, you know, it may be that you were aware of this in high school, and some of these things is what motivated you to choose this major. But I think it's worth discussing in the class, because as representatives of petroleum engineering and this department, then I think it's good to have some perspective or some big picture related to hydraulic fracturing. Have you guys had internships where you worked on frac jobs or anything? Okay, a lot of heads shaking, yeah. So, you know, you probably are all familiar, right? This is one of my favorite pictures. I don't know why it's so small. But of course, this was a composite image taken from satellites of the United States at night, and this was in 2012. So before the 2014 crash of oil prices, which changed some things. But nevertheless, you know, to give you an idea of what you're looking at, right? This is Houston here, Dallas, San Antonio, Austin, right? What's this right there? Yeah, it's the Eagle Ford Shale, right? So again, right here in the middle of Texas, or you know, in the middle of South Texas, 22 counties where not very many people live, there's somehow light pollution that's sort of on the same order as or competes with Austin and the lights of Austin and San Antonio at night, right? So that's kind of impressive that there's that much activity going on there that you can see it from space, right? Same thing in the Bakken, right? Up there. If you sort of know what you're looking for in the Permian Basin, there's a lot going on. And then over on the East Coast, there's just so much light pollution from all the big cities that it's difficult to see. But obviously, there's a big shale play out there as well, the Marcellus. Some things have changed over the years. So this was 2012. Some things have changed. I just got this one today. The images were done in 2016. I don't know. So definitely there's apparently less activity in the Eagle Ford, right? So the Eagle Ford was down here. So it's not as bright. There's certainly a lot of wells in production down there, right? A lot of that light is just due to the lights on the rigs. I can remember in about 2013 driving south on 183 from Luling, like down to Gonzales and down that way, and at night, and it was just daylight basically from all of the lights on the rigs. I mean, there's obviously some flaring that's going on too, but just the lights on the rigs can be quite bright. So yeah, there's a little bit in 2016. There's a little bit less activity in the Eagle Ford than there was in 2012. Maybe a little more in the Permian Basin, right? It's hard to tell for sure. If you look, I think Baker Hughes has an app that you can look at, like all the active rigs. What's it called? Rig count, I think, right? Yeah. So you can look at all the active rigs, and most of them are in the United States are in the Permian Basin right now. So I pulled this off today, right? You can get this kind of information from the EIA, the Energy Information Association, which is part of the DOE. and you can pull these off, any day. So I pulled this off this morning, actually. This is the total crude oil production since 1922, I believe. I guess it goes all the way to 1860, but I mean, nothing really happened to the early 1900s. And you can see that it peaked, or apparently peaked, in the early 1970, about 1970, and then kind of started to decrease, and then there's this little aberration when Prudhoe Bay, Alaska came online that took us back up, and then it's been a pretty much steady decline until 2008, when George Mitchell basically perfected the technique of slickwater fracturing, and it's been essentially all uphill since then, right? There is this little dip in 2014 due to crash in prices, but it has nothing to do with the technology or provable reserves, right? This is just purely economic there that it went down, and we're approaching the point where we'll exceed that by the end of this year. And not only will we exceed that, we will exceed the peak in 1970 by the end of this year. I kind of kid a little bit because this is sort of my research area, but if we were to zoom in on this, I'm going to get in trouble for this. If we were to zoom in on this a whole lot, so that we're looking at this little piece of the line, and then we were to take and zoom in on that little piece of the line, and then zoom in on that little piece of the line, so that we're looking at a very enhanced view. This little piece right here is due to EOR. The rest of that is due to hydraulic fracturing. In other words, I mean, I'm kidding, right? But I'm kidding, and we have a lot of EOR experts in this department, right? But we were continuously advancing EOR techniques through this entire period, and it didn't matter, right? Might have changed the slope, right? Might have changed the slope, but this is 100% due to, well, it's 100% due to hydraulic fracturing and the combination with horizontal drilling, right? Which we'll talk a little bit more about. How many of you are native Texans? Almost everybody. I'm a native Texan. I think myself and Dr. Wheeler, who you guys have probably never had a class from, but is technically part of this department, Mary Wheeler. We are the only two native Texans on the faculty, which is surprising. You'd think a petroleum engineering department would have more Texans. But nevertheless, even if you're not a native Texan, you possibly will consider yourself a Texan one day, because you're probably going to spend much of your career in Texas. You're going to probably live in Houston at some point, right? So this is the breakdown by state of crude oil production over the same time period. Texas has always been the leader, right? Alaska might have for one day passed us, right? But Texas has always been the leader, and so so Texas is the orange curve, which, by the way, I did not. That's pretty cool that it came out in burnt orange. I did not do that on purpose. I just collected the data from EIA. But yeah, so then Alaska, California, and North Dakota's also had a big increase recently. But basically, if you take all of the other 5 leading oil-producing states and add them together, they don't get to Texas, right? So you picked the right place to go to school for this field. if you look at production by play, there's a lot of talk recently about the Eagle Ford, and that, of course, that's where all the rigs are, right? I'm sorry, there's a lot of talk about the Permian Basin, right, and that's where all the new drilling activity is going. But the Eagle Ford still leads in terms of a single play. Now, the Permian Basin is broken down to the Springberry and Bone Spring and Wolfcamp, so it's sort of these right here, and if you add them all up, they might exceed. If you add them all up, they still, well, I don't think they would exceed, but they would compete with the Eagle Ford. But the Eagle Ford still is the major shale play in the United States. So these are tight oil plays. Right? Yeah, just picture of the Eagle Ford. If you have ever seen it or been down there, it covers like 22 counties in South Texas. Kind of starts up around towards Houston, but more closer to Victoria, and then has this kind of crescent-like shape down to the Rio Grande, where the Rio Grande literally stops the Eagle Ford Shale. No one's going to question that statement. Of course it does. Yeah, of course it does. That was a lame joke. But if you look at if you go back to those lights, right, all the activity stops, right? All the activity stops, and so there is a lot of interest in the Eagle Ford does continue into Mexico. And there is a lot of interest in trying to bring that area into production as well. And it's also kind of separated into sort of a dry gas rich region, a condensate region, and a oil region. And so this picture's a few years old, when a lot of the activity, those red dots represent wells. A lot of the activity was in the condensate region. These black areas are outcroppings of Austin chalk, which is part of the Eagle Ford Shale, and you can see it, and I believe you can see some of it on Lake Travis even, or somewhere out there. There's places you can actually see above the surface some of the Eagle Ford Shale. This picture's a couple of years old. It was from 2014. When in 2014 we did in fact, so I'm trying to again just educate you on the sort of impact of what's going on, so that you can be well represent the department in your industry. And a lot of times you talk about oil and gas, it's related to national security and energy security, right? Or energy in general is related to national security. And with the idea, the implication that the United States doesn't want to be relying on foreign countries for a substantial amount of its energy and have to import it. So in 2014, and again we're approaching that point again because we're approaching the total production we were in 2014. The United States actually surpassed Saudi Arabia in terms of oil production, and actually passed Russia in terms of gas production. Again, fueled by horizontal drilling and hydraulic fracturing. If we look to the future, this is again, I took this off this morning, so this is Energy Information Association, which again is a DOE organization, right? And I don't want to say that DOE is not a petroleum-friendly government entity. I mean, let's say it's petroleum neutral. That in the sense that a lot of the things they fund for research is not petroleum related, right? They're funding a lot of alternative energy developments. However, by their own admission, it's the petroleum and fossil fuels in general that are going to are projected to make up the most of the energy consumption through 2050. This is from their 2018 report, which again I just took off this morning. So while the renewables are, projected to increase, you see by 2050 it's maybe 12, 13% total. Maybe they don't fund us because they think we're doing just fine. This is a little bit older, but it's in terms of, I put this under because if you look, the natural gas is projected to increase substantially, right? And so if you look at the breakdown of gas, where's that increase going to come from? Well, it's going to come from shale and other tight gas resources, which again are brought into production with hydraulic fracturing, right? Horizontal drilling. So what is shale? We tend to use the word shale as a catch-all for any tight rock, but it's typically characterized by very low permeabilities, right? It's an organic, technically it's an organic-rich mud rock, which is characterized with really low permeabilities, like on the nano-Darcy scale. Okay. So this picture and I think the next several are taken from this Hydraulic Fracturing 101, and that's a hyperlink. So if you click on the slides, you can actually go to this. And this is an SPE paper from, I think it's from 2012. But if you go to George King's website, I think he's continued to update this over the years. And you can see kind of the subtitle: whatever representative environmentalist, regulator, reporter, investor, university researcher, neighbor, and engineer should know about estimating frac risk and improve frac performance on unconventional gas and oil wells. It's like the longest title ever. But this thing is like, or your normal SPE paper would be something like 12 or 15 pages. This is like over 100 pages. So it's an extremely good resource, and he's continued to update. If you go to his website, he's continued to update that over the years. So it's another good place if you want to learn more about this kind of stuff. So I also took this figure from that paper. So this is just a cartoon picture for the kind of historical or conventional view of horizontal wells and hydraulic fracturing. So the idea is that you drill a well, you drill a horizontal well, to give you some idea of scale, right? The well, that the vertical part could be up to 2 miles deep, right? The horizontal leg could be up to 2 miles long. Right? Typically, then you would, in a typical operation, you would go to the end of the horizontal leg. This is called the toe, right? Because this is called the heel up here because it sort of looks like a shoe, maybe, or a foot. So you go to the toe, and in a scenario where the entire well was cased, you would perforate the casing, right, with shape charges, little explosive shape charges. Everybody know what a shape charge is? No? So, just not really related to this class, but shape charge sort of looks like that. And this piece right here, I'm drawing a two-dimensional slice of it. It's three-dimensional, so this piece right here is conic shaped, like a cone. And then behind it, this is all explosives. And so right here, on this conic shape, this is typically made out of copper. Copper is a really ductile material, right? And so then what happens is the shape charge, they set off the explosive, and this copper, because it's so ductile, will begin to sort of deform in this direction like this, literally kind of from the point of the cone inward, it will begin to create a jet like this, a jet of essentially molten copper, or whatever the shape charge is made out of. And then that jet, the tip of that jet can be traveling like 10 kilometers per second. That's like satellite speed. That's fast. It's hypervelocity. So the tip of that jet's traveling really fast, and then it impacts the steel casing of the well and perforates it, causes a hole or several holes to go in. Because the shape charge is, this is just one. What I've sketched is just one shape charge, but they will be aligned in a tool such that they're oriented at certain angles, and usually like 120-degree angles around the well. Anyway, so you go to the toe of the well, you perforate the well, pump in fluid at a very high pressure, typically water, just slick water. Most shales respond well to slick water, which slick water is it's like 98, 99% water, just water. Right? Create the hydraulic fractures. Historically, the wells are drilled in the direction of minimum horizontal stress, and then the hydraulic fractures will then propagate perpendicular to that, and that has to do with just energy minimization. It takes less work to open the fracture against the minimum horizontal stress than any other direction where there's going to be a higher pressure, essentially pushing on the fracture wall due to the tectonic stresses. And so after that, you'd plug the well, and you would move up the well some distance and perforate again and pump water in again and move up the well and do it again and move up the well and do it again. Each of these sort of individual perforations and pumping stages, they're called stages. And a typical number would be on the order of 20, 30, 40 stages in a well. But I've heard of cases even up to 100, depending on the length of the horizontal well and the spacing and other things, right? The historical picture is one like this, but now we're moving far more to pad drilling. So wherever you would sort of see one wellhead at the surface, there would be an array of horizontal wells like this in each direction. And we're now looking at completion strategies on the pad level. So in other words, it's more common to not just consider completing one well at a time, but rather to take into consideration the optimal strategy to complete the whole pad such that you can get optimal production out of it. And so one of the things that's come out of that, and a lot of this work has actually been pioneered by Dr. Sharma in this department, are things like zipper fracs. So in a zipper frac, you'd produce a fracture here, and then you would move up the well substantially and produce a fracture there, and then you would go into the well next to it and produce a fracture here. And the reason for that is that if the fractures are spaced too closely to one another, right, then they begin to interfere with one another. The terminology in the industry that's used for this is called stress shadowing. I don't really love that term, but we're probably stuck with it at this point. But yeah, so if the fractures are spaced too closely, the second fracture will, in a way, sense the first fracture that you produced. And if they're too close, then they'll begin to just sort of begin to grow towards one another, like so. Right? To the extent that eventually you might even, it could be so extreme that you just get fractures going very close to the wellbore, and then you're not stimulating much of the reservoir that way. So it's, that's undesirable. So in a zipper frac, you you avoid that by, you frack once, you move far enough up the well to get out of any stress shadow of the first fracture, produce a second fracture that is anticipated to grow, straight perpendicular to the wellbore. And now you've disturbed the stress field equally. And so you can come to this next wellbore and produce a fracture that, even though there is stress disturbance in here due to the presence of these two fractures, the disturbance is more or less equal, and you can get this fracture to grow like that. There's also some other, the typical mechanism is this so-called plug and perf that I described. You plug the well, you perforate, fracture, you plug the well, you perforate, you fracture. There are some more advanced tools that you can use to put in line with the drill string that have so-called sliding sleeves. So there you don't have to perforate. That there's some type of hydromechanical device that actually opens and even can close the perforation or the holes that access the wellbore. And in those cases, you can do things, other completion strategies, like, for example, the so-called Texas two-step, which would be where you would fracture, you would move up the well a significant amount again to avoid the stress shadow, you would fracture again, and then through sliding sleeve operations, you could potentially isolate that region of the wellbore and then come in between and produce a third fracture in between them. Again, this is not commonly done, but these are things that have ideas that have actually come out of a lot of academic research in doing computer modeling of the poroelastic stress fields in any kind of inelastic model or any inelastic behavior that occurs when you produce the hydraulic fractures. Now, of course, in real life, there are lots of natural fractures all over the place, right? And so these hydraulic fractures will, in fact, grow and interact with those natural fractures, sometimes passing through them, sometimes going sort of around them, if you will, because they are three-dimensional fractures, sometimes turning and interacting with them as well. And so that's one thing, like in my group, we've done a lot of research and we've done some larger field scale simulations of very complex fracture trajectories, but we've also done a lot of very careful studies of like the interaction of a single fracture with a single natural fracture, things that we can compare to experimental results. And we develop models that sort of look like something like this. So this is a computational model that can actually predict a hydraulic fracture. I don't have time to go into all the details, but basically we're going to inject fluid there, and this is a natural fracture in the earth, and you'll see the hydraulic fracture grow and interact with the natural fracture. So this is active research that we're doing. And we have experiments to compare this kind of stuff to ensure that the computations are correct. So by the end of the semester, you'll write a code that can reproduce this. No, I'm just kidding. I mean, not to this level of sophistication. This is a guy's PhD dissertation. This is really complex because it's if you see, I mean, it's a little bit hard to see what's all the things that are happening, but if you notice, like there's a very coarse mesh out here, and then it's adaptively refining, right? So it's adaptively changing. That in of itself is not a trivial task, right? Just to go from a coarse mesh to an adaptively refined mesh. And then if you notice, there's kind of a dark blue region here that separates that, because these out here are finite elements. Finite elements have continuous fields across them. So in other words, finite element assumes that the pressure distribution and the displacement distribution in any one of these elements is continuous, right? It's linearly interpolated. Well, of course, a fracture is a discontinuous displacement, right? It's a mathematical jump discontinuity. And so you can't have a jump discontinuity in the middle of your finite element. It just mathematically doesn't work. So what we've done then also with that darker blue region is actually a different sort of mesh-free discretization even, it's something called paradynamics, which I guess I'm an expert in. But anyway, so yeah, this is like adaptive mesh refinement within the finite element region, then adaptive, sort of dynamic insertion of these paradynamic mesh-free particles that allows these discontinuities to grow. And it's coupled, this is fully coupled geomechanics and fluid flow all together. So anyway, just to give you a flavor of the, what?
1 year PhD?
Yeah, he just defended his dissertation on Monday, actually. Yeah. But that just gives you a flavor of the types of things we're doing in academia towards modeling these kind of problems. So yeah, I mean, here's another cartoon of a hydraulic fracture operation, but basically, at the surface you have these frac pumps that are on 18-wheeler trailers, right? They're enormous pumps. That's the type of sort of energy it requires to produce these fractures. Another thing I didn't really talk about was, but in addition to just pumping water, you actually pump in a slurry of water and principally sand that we call proppant. And the idea with that is that the proppant will, because if you just pump water in and shut in or eventually flow back the well, the fractures are going to close, right? And then what did you really do? So the idea of pumping proppant in is that when the fracture is closed, then the proppant, which is sand, which is very permeable, right, props the fractures open so that they remain conductive to the wellbore during production. And there's pretty good evidence that just like in a lot of wells in the Eagle Ford, just the more stages, the more water, the more proppant you pump in there, the more production you get out of the well. Yeah, so these are very big pumps. They're on 18-wheelers. And so here's a frac job from the Barnett Shale in 2006. It's an older picture, but I mean all of these, it's an aerial view. All of those red things that you see right there are trucks, right? So that's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then another 10 over here. So there's like 20-something 18-wheelers on the site. So have anyone ever been out to a frac job? Yeah. It's pretty impressive. Set of equipment, right? Yeah. And yeah, and then depending on where you are, you also have, these are all storage tanks for water, right? So that's all water being stored that was trucked in or brought in. I mean, yeah, one of the things that makes the Permian Basin work, I mean, of course, you couldn't just, there has to be oil there, obviously, but another thing that makes it work well is there is a lot of infrastructure there already in place to move water, to move petroleum liquids in and out and other things, right? And so that's why it's been able to maintain, even through the downturn, a lot of success. Also people, there's qualified people that live there. So, I mean, is it safe? Well, I think no one in this room would necessarily say it's unsafe, but there has been a lot of media things. Some of it's dying down, I think. This is my perception. Like, when I kind of first started getting into this work, there was, it seemed like every week or every day you'd hear like some, new newspaper was talking about, some of the implications of it. So, the two big things are groundwater contamination, which I think for sure the groundwater contamination thing has died down to some extent. I mean, there's really no evidence anywhere that the groundwater's ever been contaminated by hydraulic fractures. So that's died down. But earthquakes, which again I think there are earthquakes, right? That due to we call them induced seismicity, which is sort of human-caused earthquakes, but they're not due necessarily to the hydraulic fracture. You know, they're not associated with hydraulic fracturing. They're associated with the disposal of the water, okay? And some of that water, again, it's not all from hydraulic fracturing. In Oklahoma, where a lot of this induced seismicity has occurred, there is some hydraulic fracture operation, no doubt. But there's also a lot of conventional water flooding. And a lot of that water that gets put in these injection wells is also just water cut, right, from conventional water flooding. And of course, it's combined with hydraulic fracturing, but the new thing, you know, the earthquakes are a relatively recent thing, and as is all of the hydraulic fracture activity, so it gets blamed for it. And its sole blame is put on that. But if we focus on earthquakes caused by hydraulic fractures themselves, there's not a lot of evidence that occurs, right? So, I mean, the first thing is, if you know, you can go to fracfocus.org and you can look at the composition of what's in most frac water, right? It's 90% water, 9.5% sand, and about 0.5% chemical additives. And most of these chemicals are things that you'd find in your house, right? Like in your toothpaste and other things. I think there was a forum a few years ago where, I forget who it was, but someone, to prove a point, actually drank a cup of frac fluid, sick water, you know, to show that, you know, it's not harmful. Yeah. Huh? No, it didn't. I mean, it's just water. I mean, there's a good chance that there's more than 0.5% of contaminants in your drinking water, right? There's certainly fluoride. If you drink city water, there's certainly fluoride in your water. That's a known carcinogen, right? So, anyway, you know, so if you, yeah, I think this has died down a lot. Not many people try to make this claim about groundwater contamination. But you know, if you just look at the distance from where typical hydraulic fracture operations are and your freshwater aquifers, right? So your freshwater aquifers are typically above, they're within 500 feet, right? I mean, I don't think any of us, I have a water well at my house, and it's like 146 feet is where the water line is. You know, most people don't have water wells that are 500 plus foot deep, whereas your you know, your frac operations are much deeper. So the Eagle Ford Shale, at its shallowest, is 4,000 feet, right? At its deepest, it's like 14,000 feet. So you know, certainly no one's drinking water from 14,000 feet. You know, also, the way operations are done, right? You drill below the freshwater aquifers, and then you set casing and cement to the surface, right? Surface casing, always. And they did that long before they ever did hydraulic fracturing. You know why? To protect the fresh water? To protect the reservoir from the water. No one wants water. There's already enough water in the reservoir, right? I mean, no one wants any more water in the reservoir than it's already in there, because you have to treat it, right? You can't stick water in the pipe and sell it, right? So anyway, yeah, that's long been in operation. And if you if you look at some real sort of operations from map fracture treatments in the Marcellus Shale, and of course this is where this all stems from that what was that movie, that documentary, Gasland, right? Yeah, where guys in Pennsylvania would light their faucets on fire. Never mind that they could do that well before there was any hydraulic fracture activity. There's lots of methane leaks in those areas. So the Marcellus Shale is the shale in the northeast up there. And if you look, these are the blue up there is the deepest aquifer depths. And these are the fracture, these are the map fracture treatment depths from different fracture stages over certain different distances. But anyway, there's several thousand feet in between the water and any of the hydraulic fractures. And of course, many sealing layers in between. Also, does hydraulic fracture produce earthquakes? Well, again, there's two answers, and both of them are yes. Yes, hydraulic fractures produce earthquakes, but I'll show you in just a second, they're too small to feel at the surface. And then, of course, yes, wastewater injection from hydraulic fracturing operations can produce then larger earthquakes, right? But that's not necessarily associated with the fracture growth itself, right? It's something else that can be mediated by having more injection wells, or not injecting the volumes that they inject, or not injecting at the rate that they inject. All of those things matter, right? We have a lot more control on the volume of fluid and the rate of injection than we do on fracture growth, right? I mean, we're still learning with respect to controlling the growth of fractures. But nevertheless, this is a moment magnitude plot of a whole bunch of fracture stages that were taken from the Eagle Ford Shale, and you know, for you to feel, this is like a Richter scale, right? So these are all the depth, with the shallowest being about 3,000 feet and the deepest being 13,000 feet on the moment magnitude plot. So to feel something at the surface, you'd have to have an earthquake that's certainly positive, but probably more like 1, 1.5. These are all negative values, and this is a log scale, right? So you know, these values that are close to 0 are, you know, not two times smaller, but rather, you know, 2 or 20,000 times smaller than anything you could ever feel at the surface. Right? And so these are from the hydraulic fractures themselves, and again, it's really a different thing when you talk about wastewater injection. There has been, you know, earthquakes associated with wastewater injection, particularly in Oklahoma, that you can feel at the surface, and you know, we need to do a better job at predicting when that's going to happen, so that we can avoid those things. And that's also an area of research called induced seismicity. So anyway, we'll stop here today, and we will